Hey everyone, Akil from Oxford Academy here. This is part one, or problem one, in a series where I talk about related rates problems and how to solve them. So, part one. A snowball melts such that its volume decreases at 8 cubic centimeters per minute. Assuming the snowball maintains a spherical shape as it melts, how fast will the snowball's surface area change when its radius is 5 centimeters? Now, let's go ahead and translate this problem a little bit. Volume decreases means that we're given the rate of change of volume, or how the volume changes with respect to time. And the way we indicate that when we do related rates is we use derivative notation. So we say dv dt is going to be equal to not 8 cubic centimeters necessarily, but negative 8 cubic centimeters. And the reason why it's negative, because if we go ahead and draw it on a graph where this is volume and this is time, if this was our volume function, let's say, notice that it's a decreasing function. Okay, well, I mean, this tangent line works too. Just ignore this point right here. So, if you notice, this is a decreasing function. Its volume is decreasing. But if we go ahead and look at this tangent line, the slope of the tangent line is negative. So, by definition, the rate of change, or not by definition, just by proof, the rate of change must be negative whenever some quantity is decreasing. So we have dv dt, negative 8 cubic centimeters per minute. Now, what do we do next? Well, we know that we're looking for surface area, and we also know that the radius is 5 centimeters. And we also know it maintains a spherical shape. So, essentially what this problem is telling us is that we need to somehow go from volume to surface area by using some formula for a sphere. So, what formula do we need? Well, we need the volume of a sphere formula. We know that's just 4/3 pi times the radius cubed. Now, you're probably looking at this and you don't really see surface area. You could do some algebraic manipulation to get volume in terms of surface area, but that's not really necessary. But what we can do is we can actually find a bridge between volume and surface area because there's no direct connection in this formula. So, what can we do? Well, let's go ahead and use this problem and implicitly differentiate it. So, we're going to get d dt just like this. Now, whenever we do implicit differentiation, remember, any quantity that changes with respect to time, we have to put a d dt, or dv dt, or dr dt in this case. And I'll show you. So, by doing implicit differentiation, we get dv dt is going to be 4/3 pi, these are constants. Now, r is changing with respect to time. If the volume is changing, then the radius has to change. So, because 4/3 and pi are constants. So, by doing implicit differentiation, we get 3r squared times dr dt. That is how we do implicit differentiation. So, simplifying this out a little bit, we get that this is equal to 4 pi r squared times dr dt. Now, we know dv dt, we know what r is, because it says right here the radius is 5 centimeters. So what we can do is we can solve for dr dt and hope that takes us somewhere. So, by solving for dr dt, we get dr dt is just 1 over 4 pi r squared, just dividing the 4 pi r squared on both sides, times dv dt. Now all I have to do here is just plug in our known quantities, and this gives us 1 over 4 pi times 25, because 5 squared is 25, so we get 25. Multiply that by the dv dt, which is negative 8, so you get negative 8. And all we have to do here is we can actually go ahead and simplify this. The 4 cancels out with an 8, leaving a 2 on top, and we get that dr dt is equal to negative 2 over 25 pi. And the units for this are centimeters per minute because radius isn't measured in centimeters. So, what can we do with this? This isn't our final answer because we're actually looking for ds dt, or the rate of change of surface area with respect to time. So how can we do that now? Well, we know what dr dt is. We also know what radius is. Let's try using the surface area formula this time. So, the surface area of a sphere is 4 pi r squared. Alright? Let's try implicitly differentiating this. So we get d dt on the outside. So now all I have to do, doing implicit differentiation, we get ds dt is equal to 4 pi, and implicit differentiating r squared gives us 2r times dr dt. And this is equal to, multiplying 4 and 2, we get 8 pi r times dr dt. Now all I have to do here is just plug in our known quantities to get what ds dt is. So we know what radius is, and we know what dr dt is. So ds dt, that's going to be 8 pi times 5 times dr dt, which we know is negative 2 over 25 pi. Now, 8 and 2 can multiply into 16, pi's cancel, and 5 cancels with 25 once because 25 is 5 squared, so that just leaves us with the 5 in the denominator. This gives us negative 16 over 5, and the dimensions for ds dt, surface area is measured in centimeters squared, and t is measured in seconds, or sorry, not seconds, minutes. So, let's go ahead and, did I say seconds here? I meant minutes, sorry. So, we have negative 16 fifths centimeters squared per minute. So if we wanted to write out a verbal answer for this, we get the surface area decreases, because we have a negative sign right here, decreases at 16 divided by 5 is the same as 3.2. 3.2 centimeters squared per minute. And that's our answer. Done. So that's part 1 of this series. I hope to see you guys in part 2.